Hello, everyone, and welcome. This is Professor Thayer with you here today to talk to you about an introduction to machine learning. This is the third lecture in our three-part series. So we'll talk about the neural nets today. So let me go ahead and share my screen and let's get started. All right, so as we mentioned, today's topic of discussion will be the deep neural networks and how to build these in TensorFlow. So to give you an overview of what is happening here, first of all, we will review some of the key concepts that we've talked about in some of our other sections, and also just preview some of the concepts of the deep neural nets in a qualitative way that we will be taking a look at in more detail. We will then talk about the perceptron, which is the simplest unit of the deep neural nets. It is taken from neurons, and we will consider how we might take a single perceptron and then build multiple perceptrons into a network for more complex decision making. We will then do a step-by-step example of how to build a neural net. This will focus on how to actually write the code and implement this in TensorFlow so that you will have some hands-on experience on how to do this. And then we will take a look at an exercise that I've prepared for those who have an interest in getting into working through this a little bit more. So let's get started. So then just to review some of the key concepts that we've been talking about in the machine learning process, there will be several stages. First one, we'll need to collect data, preferably large amounts of data for training your model. Then we will generate some kind of a hypothesis. What is it that we want to study? And what do you think that the hypothesis might want to be? What is it that you might want to predict? The next step will be choosing a model for actually carrying this out. Now, we've talked about linear regression in quite a lot of detail the last time, and we've seen how we can do some fitting and so on with the linear regression in order to have that happen. We can also use decision trees, a single tree, or we can put multiple trees together to make a forest. We might also think about putting together Markov state models to build this up. In a sense, the deep neural nets is a more complex version of the Markov state models. And then also we could consider many different architectures of these deep neural nets. And these are just some of the kinds of models that one could use. Today, of course, we'll be focusing on the deep neural nets and how those work. In the process of the overall machine learning process, oftentimes there would be some iterative refinement of the model buildings. So for example, some of the choices that we'll be talking about today are, how many nodes to choose, what decision-making algorithm will be used inside of each of those nodes, and so on. So there would be some iterative refinement in terms of optimizing the kind of model, or perhaps even choosing a different of the models that we've discussed in order to solve your problem, and then working on that until you have come up with something that is suitable for the kinds of questions and testing of the hypothesis which you have generated in the earlier stages, in order to then be able to have a model that predicts the outcomes that you wish to predict. So of course, some of the key ideas here have to do with the data set. So we would need to divide our data set into a training, validation, and test set. The training set ideally will be large so that we will be able to span the needed parameter space so that we can get some training up and have that done well without having any kind of overfitting and so on. The validation set would need to be labeled, that is, knowing what the expected outcome is. We wouldn't let our machine know about that, but we will run our trained model on the validation set to find out what the model says the answer is, and then we would compare that against our own answer and see how well the model does. If it's not doing so well, that suggests we should go to the iterative phase of improving the model with some of those ideas we have just been mentioning. And finally, when the validation set is to our satisfaction, then we can use our model on the test set, which is the actual data, to make the predictions where we don't know the answer. And we would then expect that the level of confidence that we have with the validation set would extrapolate over to our test set. Some of the challenges of machine learning include insufficient quantity of training data, non-representative training data, poor quality of the data, the overfitting problem, and the underfitting problem. We have seen a lot of these examples when we talked about the linear regression that we talked about the last time, that is trying to fit a line to some data. And so some of the major problems one can have is, you don't have enough data, or the fitting problem. Perhaps somebody looks at this and says, oh, I'd like to fit the data better. And we saw an example of a higher order polynomial that hit every single one of the data points exactly, but of course was of much higher level of complexity than was reasonable. And so that, of course, is an example of overfitting in an exaggerated sense. But we would also just want to make sure that the model is reasonable in those regards. So let's take a look in a qualitative kind of way as to how a deep neural net will actually learn. So we'll look at this in a qualitative sense right now, and we'll of course get into more of the details as we step through the next section. So one would have some task at hand. Perhaps we are trying to classify images where the choices are flowers, cups, cars, and trees. For humans, this would be very easy to tell them apart. However, for a model, we would like to have the model be able to somehow take some input image and tell us the type of object that it is. So here we're going to have an image of a lily, and we want to be able to have the machine learn this. So let's just understand a little bit about what's going on here. We would be setting up some layers in order to do our training and to have the parameters. In this case, we have 4 different ones. These are the ReLU, the ReLU example. And so we'll see some more about what different kinds of models you could plug in here, basically equations for decision making. And so in this case, we are using 4 layers, which is being represented by this picture over here, having 4 layers. And so we begin with the input image. And so what will happen is the machine will optimize the parameters to see something about this, and then it will pass the information on to the next layer, which will then take some inputs and continue the process. Now, what we notice is in the beginning, there's a lot of things that are relatively able to be discerned by humans. For example, this picture right here, the input, we can clearly see that this is a flower, a lily flower. And then, but we may see that things are getting a little bit more complicated. One might look at this and say, okay, so I could see that it's learning the shape of a lily here, perhaps, although it looks kind of abstract. And if I hadn't seen this input, I may not have guessed that. And as we see, it's getting increasingly abstract in terms of the way that it is processing the data. So one of the take-home messages here is that the machines are not necessarily going to be learning on the things that we see, but it will be optimizing in the parameter space within the constraints that we give it. So it will go through these 4 stages of pulling out information, optimizing the weights of the various things that it is optimizing, and then we will eventually come to an output over here, which the output in this case would be one of these classifications. So let's take a look at the difference between deep learning and machine learning. And we did talk about just learning in general, and looked a little bit about the deep learning in a bit more detail. So this is a little bit of a review of that. The idea here is that in the deep learning that we are going to have a number of the hidden layers that are going to be doing the learning, whereas in typical machine learning, that those it's going to be much simpler. It could be a decision tree where one simply has yes or no answers to a series of questions. But you see here in the machine learning, typically the information is all present and available for the user to see, and it would be available in a human interpretable way. Whereas in the deep learning, it becomes much more abstract, in this abstracted learning space where each of the neurons is computing something in to optimize some functions rather than to focus on some reason or some attribute, some feature that is recognizable by humans. Machine learning tends to do well with small data sets, whereas the deep learning is going to require much larger data sets, mostly because it has so many more parameters. The machine learning is relatively quick to train as opposed to deep learning, which takes much longer. In machine learning, we need to try different features and classifiers to achieve the best results. So that becomes something that's very important in terms of the input, whereas in the deep learning, one can simply just throw in whatever information you have and then expect the machine to figure it out by applying the weights. So even if you apply some information that's not really that important, that will be fine for the machine because it will simply just put an importance weight on it to be very small, and so effectively it's washed out. The accuracy of machine learning will plateau, whereas the deep learning accuracy is unlimited, assuming that the data set is also not limited. So in the limit of adding more and more data, it's possible for the deep learning machine to become increasingly accurate. So now let us get into a little bit about the actual perceptrons in the deep neural nets. How do they actually work, and how can we build up some kind of a structure that would allow one to actually calculate something? To give you a little bit of history on this, in fact, the artificial neural nets have been around since 1943. This was right after World War II, and the neurophysiologist Warren McCullough and the mathematician Walter Pitts, working with him, had put out a seminal paper called A Logical Calculus of Ideas Immanent in Nervous Tissue. This work proposes the idea that simple neurons could be organized into higher order so that it could think. And so that was where the idea of having a perceptron, an individual decision-making element, could be used to make simple decisions, and that those simple decisions could be linked together, similar to how they believed that the neurons could be put together in order to do much more higher order kinds of thinking. In the 1960s, people thought that we'd soon be conversing with intelligent robots. This is borne out in a lot of the cartoons and other popular culture items that came out around this time, where there are robots running around the house that are family members that are helping out with all the tasks and these sorts of things. But in real life, of course, this had not happened, and so people started to have a waning interest in this field as it felt that it became increasingly unachievable at that time. Funding fell and research in this area somewhat dried up. There was a resurgence in the 1980s when artificial neural nets were revived as researchers became interested in exploring things about neurons and decision-making and prediction. This was just a short burst, and then after the work on that area was finished to their satisfaction, the ANNs largely fell back into a dark age. However, there seems to be a resurgence in the artificial neural nets these days. You may have noticed this anytime you pick up your phone, use an app, get a suggestion from Amazon, use Google products, and so many more ways in which artificial neural nets are contributing to our daily life. Some of the reasons that we now believe that artificial intelligence and neural nets are here to stay include the much larger data sets that are required to do the training. We have many data sets available. There's repositories for these things. That resource has become much larger and very accessible to the general public and, of course, to researchers. We also now have an improvement in the compute power for training. This is largely due to the fact that our GPUs have then have evolved. This is the graphical processing unit. They came up in the context of gaming to process the vectors to improve the way that the games are displayed, but it has turned out that they do not care what the content of the vectors are. And we talked about TensorFlow works largely with data represented in vectors and matrices, or even as a tensor, as the name suggests. And so GPUs are extremely useful for working with this kind of data. They are exactly and entirely suited to do this. And this has driven what we can achieve forward by leaps and bounds. Also, the success of ANNs can be regularly seen in the many household devices and services which run off of artificial intelligence. So in the biological context, on the left-hand side, we see a depiction of a biological neuron where we have a nucleus surrounded by axons and dendrites, essentially as a series of input and output. And so we have this idea that there would be some kind of inputs, and in the nucleus there would be some kind of a decision-making black box process that would decide whether or not the neuron would then fire to push the signal along to the next neuron or neurons. So this is, of course, very much akin to the perceptron, which we will take a look at in the mathematical sense coming right up. So the idea here is that one could put together a number of neurons to make something much more complex. This is an image of multiple layers in a biological neural network taken from a human cortex. So in fact, these neurons are all linked together, as we can see from the interwovenness of their axons and dendrites. The cortex, of course, is the frontal part of the brain, which is responsible for higher order thinking, and it is believed to be most highly developed in humans. So if humans can do this with individual neurons to build up ways to think, why not build up artificial intelligence in a similar way? So the perceptron is the building block for the neural nets. Here we see a depiction of a perceptron. We have some inputs. This here shows 3 inputs, but of course there could be any number of input with 1 or more. And then something will happen in here, and that will determine an output. In the simplest version, the output may be determined by this step function right here. It will output a binary 0 or 1 based on this criteria. We will sum the weight times the input value, xj. So xj could be x1, x2, and so on. And then we will sum all of these together, and we will ask the question, is it above or below the threshold? So this gives us the idea that there are some numbers that could be changed. Of course, the input values should be the data as it arises. But what we can change is the weights. So we can adjust the weights as a tunable parameter along with the threshold value to make this sum, and then the answer is it above or below the threshold, ultimately to give an answer that is commensurate with information that is already known. So this is the idea as to how we will train, and this is very much linked to what will happen in the backpropagation algorithm. So there are a number of things that one could do here. So here we are talking about the perceptron using the step function. This equation here is exactly the same as the one we have just been talking about in the previous slide. And so we see that we have some inputs, and those inputs have some tunable weights. We will sum up the product of the x1, x2, and so on times their associated weights. This, by the way, is the dot product. And then we will sum up all of those products. And then we will ask the question, is it above or below, yes or no, which is the step function for a binary signal. But why stop there? Why not use some other way to make the decision? And so the idea here is that one could plug in any number of different functions. So here's an example of SGN sign function, not SIN, but SGN, to represent the idea that it could tell us is something less than, equal to, or greater than 0. Notice that this, instead of being binary, is now ternary. So of course we're not limited to doing ternary, but we could do whichever one we wish. You could even make up your own function to make the decisions. But here we will return -1, 0, or +1 based on this information. So one of the things that I just wanted to point out here as we are doing the perceptron is this equation here. Now this may not look the same as the one we have been using, but in fact, actually this is. So I'll point out that X could be a vector that contains all of the input X values. And so we would need to do the transpose of this if it is a column vector instead of a row vector, which is historically the preferred way to do it. And so then what we would do is we would multiply each of those times their associated weights. So x1 will be times w1, x2 will be times w2, and so on. And so we can write the weighted sum then as z equals, and then we do the transpose of x so that each of the x's lines up with their associated weights, and then we would take the dot product. One great thing about this is that it means that we can plug into the framework that already exists to calculate these things really quickly. For example, NumPy has wonderful capabilities for working with arrays, and the Python code has actually been ported over to the C code, which runs much more efficiently than the Python code. So we can take advantage of all of those things if only we would simply just represent it in the correct notation. And so this is giving us some idea as to how that is happening. And also this should help you recognize some of the notation you may find in some of the readings that you're doing. We can perform logic with perceptrons. So for example, we can bring together neurons that are giving binary outputs, and it can be shown that the binary outputs can be combined in order to make logic gates, and or not are the most simple of these. And here are some examples of how this logic can be combined in order to create logic gates. So this is terrific. Now we have some buildup of the neurons which could actually act as logic gates. So this is leading us in the direction of building up from an individual perceptron to a whole network. So if we take a look on the left here, we see that here we have some nodes to represent the input layer. Then we will have the heavy layer. The reason why we have all these arrows is because this says for the data x1, for example, this x1 data would be fed to all of the neurons in the next layer. The same is true with x2. It will be fully connected, transferring its value to each of these nodes in the graph. And so then in the hidden layer, these layers will then have a perceptron, and they will make a computation to decide what will the output be, and the outputs of these will then be shared with the final output layer, which integrates the information from the input that it received to make the final decision about what the output value of this will be. So one could get a yes or no answer by saying, like, what does the final value look like compared to a threshold for some data set. But why stop with just one layer? This suggests a more complex way that we can build these up. Here, this one is showing x1, xi, all the way to p. So we could have as many inputs as we wish. And each one of these inputs then needs to transfer their data into some perceptron. So each of these nodes is holding a perceptron. Each of these then would have the input x, the x value, and the information to make decisions. And then it would make an output which it would pass on to the next one. So here we are not actually literally showing it. We have this by the ellipsis, the dot, dot, dot. So of course there could be more than one layer. So we may have a second layer, in which case the information will be passed from the first layer to the second layer. Each of these layers, incidentally, could have any number of neurons in it. And so we will talk about how this could create training problems, because if you add too many neural nets, perceptrons, then you will have so many parameters that it forces your data set to need to be larger. The idea is then, after you have passed it through as many of these layers as you have declared, that then they would go over to the final layer, which is the output layer, which will create a single answer that it sends out. So we have the input being X, the independent data observations or the independent variables, and Y being the predicted output. So what we have then is the input section, the hidden section, and the output section. Why is the hidden layer called hidden? Well, the reason why is because the data in here becomes abstracted, just like we saw when we were doing the image processing. The things which are being optimized in this section may or may not be human readable, and that's really irrelevant to the problem. Really, the question here is about optimizing on whatever the machine deems is the most important for getting the correct answer. So the hidden layer is hidden in the sense that it's not a human graspable feature anymore. It's working in an abstract kind of a space, and that's what's hidden about it. Notice that in plain machine learning, one really doesn't have a hidden layer, because you might go from input to output, for example, answering yes or no questions, which is really quite different than optimizing weights in an abstract space. So that's what we mean by the hidden layers. And then finally, we have the output layer, which will tell us the output of the data, that is the prediction. Next, we come to the backpropagation algorithm. This is very important for training. In fact, the backpropagation algorithm has been around for quite a long time. It came out in 1986. And so what one is doing in the backpropagation algorithm is training. When we say, okay, let's consider just a step function example. So let's say we have some weights times the x1 input, and then you have some other weight times the x2 and so on, and they will be summed up in order to check whether it's above or below the threshold. Now, did you ever have the experience when you were doing an experiment and you looked at it and you say, oh, it's just not quite right. If only this one were a little higher. That's really what I think it should be. I must have made a mistake. Let me do that again, and try to make this value be higher next time. Basically, that's what backpropagation is doing. It's looking to see how the model was incorrect according to the expectation for the output, and then what it can do is it can make a change to the tunable parameters. Of course, we can't change the data, but we can change the weights that are associated with it, and we can adjust the threshold in order to get a sense of where the threshold ought to be. So in the training stage, one of the major questions that we're asking is, well, what should the increment be? That delta t for, or that delta perturbation for the training. So if the delta is very, very small, as we saw last time for doing the regression, the problem with that is that you will need to train many, many times for the parameter to change at all. Right? If you're changing it out in the nth decimal place, yes, you might be moving in the right direction, but your fudge factor may not be large enough to change the outcome and see the effect that you wish to have. On the other hand, if you're training with a step size that's much too large, you can be jumping over the minimum, as we saw last time. And so one needs to look for a step size in the training that's going to be follow the Goldilocks principle. It's just right, not too big and not too small. And so that is what we will be looking for. In a more formal sense, we can talk about the backpropagation algorithm in terms of some of its properties. It handles one mini batch at a time. So you may have some instances and some data, and you would cycle through that. Each time you cycle through the data, it's called an epoch. And so one may cycle through those multiple times. Why would you cycle through the data more than one time? Well, this might have to do, again, with what we were just talking about the step size. One may be on the more cautious side and make a smaller step, especially when the data points are making conflicting advice about what ought to happen, if you ought to increase or decrease by your delta for your training step. So if one is saying, okay, increase, and the other one is saying decrease, you may have some problems and you may have some issues reaching convergence. So what you can do to help with this is you can decrease your step size for the training, so that you would not make too much of a change to the parameters as they are, so that you don't go overly large in your steps. And we may need to do this multiple times, which is why we would cycle through our data multiple times, which means that we would then have multiple epochs to do the training. So that's why you would do that. Each mini batch is going to be passed to the input layer, and then that is going to be sent along to the other layers, and the information will move on through the graph to move the information from the previous layer to the next layer until we reach the end, the final prediction. We are also going to measure the network error using a loss function that compares the desired output and the actual output of the network. We do this regularly in molecular dynamics when we are looking at the RMSD, root mean squared deviation. This is essentially the same formula for the root mean squared error, just that in general, we may not be measuring with respect to some specific metric, like in RMSD, we're measuring the distance. It may be more abstract. The distance between some vectors, for example, may be more appropriate, but same idea. Then we're going to compute how much output connection contributed to the error, and so we would be needing to make the next step, and we will need to apply the chain rule. We talked about the gradient descent at length last time. The gradient descent can be solved by applying the chain rule depending on your function. And so then we would be applying that information to figure out which way, not which way to minimize your Gibbs free energy as we would with NMD, but which way we can change the parameters in order to make a better fit for our model. Maybe we need to lower the threshold, and then, oh, we have the correct threshold, we have the correct prediction because the threshold was lowered, something like that. And finally, the algorithm that then measures how much of the error contributions came from each connection in the layer. And then we can use that information to perhaps change the architecture of our model itself if that may be warranted. So at the end of the day, training a model is really just a minimization problem. We can use the gradient descent that we have discussed already. This is very useful for energy minimization in molecular dynamics. It is very useful for training the linear models and the linear regression, and also gradient descent can be used for this as well. So we're going to have the del of the Laplacian, which we see is represented by this operation here. So we're going to have some data set with our theta parameters of F0. We're going to have some distribution over theta. We'll have our learning rate or step size, and the epochs is the number of steps. And so we see that we have this very simple algorithm that is going to produce our results. So we're simply going to cycle over all the epochs. We're going to evaluate how we can improve the model by looking at the gradient. That is, if we switch something, and then we may change up these steps using our training parameter to make a tweak in the actual values that are associated with the weights and or threshold. And then we would cycle through this for however many epochs that we had, and of course also cycling through each of the data points in there. Finally, we will return the thetas. These are going to be the outputs of the model prediction. So again, this is just to remind us of how this works. So the activation function, we talked about using an activation function that is a step, that is a 0 or 1 that has some cutoff at a threshold. But why stop there when we could perhaps use some more sophisticated ways of making decisions? So we could also use a sigmoid, we could use a tan function, we could also use the value model as well. Any of these could be appropriate choices. Now, when we need to solve the gradient, of course, being able to take the derivative of these is imperative. So that's why we're just looking at the derivative over here, because that could help us get some idea as to how easy that is going to be. So then we can start to build together these more complicated perceptrons. Again, we'll have our input layer with the input data. You may also have some information here. So this sort of acts like a number to multiply the whole thing by in order to modify how it's working. Then we would have our hidden layer of one or more nodes. And then finally, we would have the output layer, which makes the final decision based on the processing of the data through the previous layers. So perceptrons can be used to classify objects. Basically, what one can do is one can take it so that it will be inputting some inputs. Here we are also using some bias neurons, some constant. And then we are going to have the outputs over here in the output layer. These are going to make some predictions. So for example, it may make a prediction in the form of a numerical value from 0 to 1, where we have some associated things. So for example, if we are classifying clothing, what we might do is have various articles of clothing being represented by some range of within the output range. There are a number of architecture choices that can be made for the perceptrons. Here is a summary of some of these ones that we have seen or that could be used. So the number of input neurons would be able to be changed up. The number of hidden layers, we saw that one could have one layer or multiple layers. We would also need to make a choice about the number of neurons per hidden layer. So the idea here is we're starting to say these are the things the user needs to specify that are going to affect the quality of the outcome. The number of output neurons could also be used. We also have the hidden activation layers. Which model are you going to use? You may choose to use the value model, the sigmoidal model, or any of the other models that we have presented. We also have the output activation, none or value soft plus. Could be chosen. So what these are going to do is basically be some of the functions. The soft plus or soft max can be used in order to normalize your data such that it is always going to be scaled to output within some max and min. Usually using 0 and 1 are chosen. And then you just see within that range which item it matches up to. And then finally, we would also need the loss function, something to compare to figure out how well we are doing. So suppose you wanted to actually run this, what implementations are available? Well, Keras is really the workhorse for doing the training, and it's not surprised that TensorFlow has made the choice to include Keras into its package as the main one to do this. So you can use it as a standalone. These are some examples of programs that can be used in order to work with this. And also we have the TensorFlow.Keras, which is the version which has been incorporated into TensorFlow. So if you download and install TensorFlow using your pip install or your conda install and so on, then you will have TensorFlow in your workflow available for your use. So I thought it would be useful to go through a step-by-step example of how to actually build a neural net. Here we have the classification task. Suppose you want to classify these clothing items. So here we have some pictures in 28 by 28 pixel form of some fashion and accessory items. And the goal of the machine learning is that we want it to look at these and figure out what sort of item this is going to be. So the first thing you need to do is you need to load the MNIST dataset. Remember, it's to import all your libraries at the top of your script. So you would need to import your TensorFlow and anything else you're going to need. You may also import Keras if you're going to use that separately. And so then the next thing we're going to do is we're going to import the dataset. So here is the syntax for what we can do. This will download it from their site. And then we're going to break this into your test and training sets. So this here is going to do the mapping. We're going to store some data into each of these things. Then we can check the dimensions and the data type by using the .shape and .dtype. These are part of the Python package, which have been incorporated into TensorFlow so that you can get out the information from these. This is the beauty of object-oriented programming. Our data set may need a few more edits. We have a test set and a training set, but no validation set as we have done it so far. So we would like to create one. We can use the gradient descent so that we need to apply for feature scaling. So we'll scale the pixel intensity to be between 0 and 1 by simply dividing out by the maximum 250, so that basically they all get turned into percents on a scale. So here we are going to get the X and Y value data. We have the validate and train data sets built off of the previous ones, making these modifications that we have just noted. It's also useful to add the labels to the data set. So what we're going to do is we're going to put out the class names. So of course the output, the raw output from the model will simply be some floating point value. And so, well, what does that mean? We're trying to classify objects. What does that mean? So what we can do is we can have a scale, and that scale will then have, for example, maybe t-shirts is represented by an output of 0 to 0.25, and then trousers may run from 0.26 to 0.27, and so on. So one can then just interpret the output by looking at what the number is, and this conveniently can be used to map these things onto this. So this is a really important slide. This is step 2, how to actually build the model itself. This right here really sets up the architecture of the model that's being used. Here we're going to use a sequential model from Keras, and we are going to basically put in our layers. So our input layer is going to be a 28 by 28 pixels. That's the size of the picture. Then here we are going to have the activation. Notice that we have chosen to use 300 perceptrons in here, and the type of perceptron they're going to be is the ReLU model. We also then going to have another layer, 100, with 100 perceptrons, and this is going to use the same type of training, the same type of model in it. Notice that these are values that could be chosen by the user, how many neurons could be put here, and this is how you would specify that. And finally, we're going to have the output layer. So this will consist of 10 perceptrons. It will take the information directly from the previous layer, and then it will apply the softmax, which is basically just going to be a data normalization. So that's what this code does, and this could be a good way for you to get started coding up. Now, there's a few tips on Keras Standalone and Keras and TensorFlow. So Keras has actually been around for a while, and so of course there are many great resources. So we don't want to make waste of that. We can use many of the things that are already out there simply by just recognizing that there are some Python programming changes that need to be taken a look at or taken into consideration if you do choose to do that. So for example, we can do the imports using the dot notation. This is just a few examples of that. These are Python skills, so hopefully these are familiar to many of our viewers, but if not, we do have some videos that deal with Python help that could get you up to speed on the object-oriented programming approach to Python programming. Next, we can check on the model summary. This is useful to get an overview of what's going on in your model. Very useful if you have tried out a variety of different ones and you want to keep track of, which one is which. You can use the summary to find out the information about a particular one. Finally, we need to compile the code. So we would do model.compile, and we would then be using a kind of an optimizer and also some accuracy metrics in order to determine whether or not the training has gone fine. This is useful to look at because it means that we have gotten away from the TensorFlow sessions. Now, if you do read Aurélien Guérin's earlier book, or in fact any of the earlier literature on how to do this, and also a number of tutorials, there will be this concept of sessions. Now, sessions is really a pain to work with because basically you need to manually set up the graph, and then you need to run the session. And so a lot of people complained about it, and the developers have done away from it in the latest version of TensorFlow. So do just be aware of that, and just be sure to focus on working on the kind that's the better one. So that means you should be using TensorFlow 2.0 or above and not earlier, or else you'll have this headache to deal with. So here is training and evaluating the model. We see, for example, that the loss is decreasing over time, which is exactly what we want to see. We can also use some plots to evaluate the model. This is just using pandas. One can plot using Matplotlib. There's also Seaborn. Either of these can be used to make these. And this works out really well if you're working in the Jupyter notebooks, because you can graph right in the script itself. So then finally, we are ready to predict with our model. So what we can do then is we can use the predict to actually ask the model to provide us with the output that it associates with the input value. So if we have done this correctly, then we should have some predictions. Notice that we had some outputs and we have some numbers here. So what one can do then is one can use this information and compare this up with the inputs. Of course, we need to keep track of those annotations. So we had that vector with house or car or boats or all the different types of clothing. That's what we are going to compare to in order to determine what it is. Now, here is some recommended reading for you. This lecture today has been loosely formulated around early in Neurons, chapter 10. Most old slides are taken from this, so I highly recommend reading this book and also following along with this information here. Note that this is an early release of the new book, so that's definitely a good one to get your hands on. So I've prepared some exercises for you to work on today as usual. This will be an end-to-end house price prediction project using the famed California housing data set. So we would use some census data from California and try to predict the value of housing based on the number of rooms in the house. So to do this project, these activities will take you through doing all of the steps. We'll have the learning objectives that you will learn the fundamental TensorFlow concepts. You'll use linear regression class in TensorFlow to predict the median house range and how this pans out over each of the city blocks based on one input feature. So then we could evaluate the accuracy of the model's prediction using the root mean square error, or RMSE, and we can improve the accuracy of the model by tuning its hyperparameters, that is, have it undergo the learning process. So the process that we will use in this lab is the same as the process that we have been using all along. We'd load some libraries in a data set, we examine the data, there would be a model being built, we may wish to tweak the parameters, and then we would test the model. And then after that, we can go back to the drawing board and build the model again based on whatever adjustments we needed to make. These are the steps of model building: defining the features, define the target, configuring the linear regression, define the input function, train the model, and then evaluate the model. There are three options of ways you can set up and run today's lab. The first is you could run this on a Jupyter notebook, and in fact, I actually have a Jupyter notebook linked for you that you can just use. So the bad thing about this is that you don't get the experience of engineering up all of the different aspects because you'll already have it done for you. But of course, the good thing is that this is probably the simplest way that you can just get started and execute this right now. You can also download and install Anaconda and install TensorFlow. This has a little bit more overhead in terms of time investment, but if you are going to be running machine learning, I highly recommend that you do this. The other alternative would be to download and install Python packages. This is not my recommended way of doing things, but it is also a possible way to do it. So for example, you would have a number of package dependencies, and if you had done this with Anaconda, then you would not have needed to worry about all of that because all of the supporting packages are automatically installed. And when you run it online, you don't worry about any of that. It all happens behind the scenes. So then these are the links to today's labs and exercises. As usual, we have a location on our Google Drive. This is the whole Google Drive link. And I've also created the short one at the tiny URL, which does seem to continue to be stable. And also there is my video on the machine learning housing project. And here is the exercise on machine learning and using the Google Colab. So you may wish to use this way of doing the lab instead. All right, well, thank you so much for joining us today. I hope that this has been helpful and instructive to you as you think about how to do some machine learning and work into one of the first or early machines that you actually tried to build yourself. Please consider working the examples that have been shown in the slides here, and also please take a look at some of those exercises we've put together for you so that you can get the best out of this. All right, thank you so much for joining us, and we hope to see you soon. Thanks, and enjoy your day. Bye-bye.